Welcome to the third and final interaction session of this course Computer Vision, and I will be happy to answer your queries on the topics you are presently going through. What I understand that this is the 10th week of your course, so most likely you are going through classification and clustering techniques. So let me have the queries. If you have any, please send me those queries. So to start with, I have a few questions to answer what is already posted in the Google Doc. So there was questions regarding the popular computer vision library, what you can use. I mentioned already that there is a library called OpenCV, and it is available in different programming languages. Particularly, it was available in C. It is available in C, C++, and also you have Python, where also you can get these libraries. So I hope when you learn programming, if you are really working on some projects of computer vision, you will be using this library. You should be familiar with these libraries, one of these libraries. Some of you may work with MATLAB also and use MATLAB functions for many of the implementations that are available in MATLAB. And sometimes for developing algorithms, MATLAB is easier to handle with in that framework. So that was the first question. Then there is another. I don't know whether it's a question or remarks, or it is just saying that about the texture feature descriptor, about Michael Unsert's work, where sum and difference of texture feature, it is not properly phrased, and also it is saying MATLAB code. So I have nothing to do with MATLAB code. So if you are learning, you can implement it. Only thing is that there is a paper by Michael Unsert, who is a very one of the frontline researchers in this area from Germany, and it was a very old paper. I think it is in 1988. Transactions on pattern analysis and machine intelligence. So this paper suggests that an alternative to the texture feature descriptor, what we discussed in this course, that is use of co-occurrence matrices. So instead of using co-occurrence matrices, it considers use of sum of two random variables, sum and difference of two random variables, and the joint distribution of these variables. So just to explain the fact a little more, that that co-occurrence matrix is nothing but it provides you a joint distribution of two random variables. One of the variable is from a particular type of site, and the other variable is defined. So these two variables, they have some spatial relationships, as we have mentioned, some directional relationships, and they are joint distribution of values in the feature space. For example, in the brightness level, if you consider brightness levels are feature of the for describing this kind of texture. So the joint distribution in that feature space for these two random variables, that has been considered in when we use a co-occurrence matrix, build a co-occurrence matrix, and then from the co-occurrence matrix you define different measures which are used particularly for features. That we have discussed. You may go through those lectures once again. Now, instead of joint distribution of these two random variables, we can consider distribution of sum and difference of these two variables. So that is also joint distribution. And what Prof. Professor Unser has shown that the performance is comparable if you use the co-occurrence matrices. And there are certain other mathematical interpretations. You may go through this paper, you may give a search and find out what is written in that paper. So, it is more important to understand the theory than using any code blindly. That is my suggestion. So, please go through the paper and understand the theory in that case, if you are interested to know what it is. So, that was the second question. Then the third one, it is asking about my opinion on computer vision in autonomous driver assistance systems. Okay, it's very general. As you understand, computer vision is very much necessary for any kind of autonomous system which uses the visual feedback. And naturally, if you are developing a car with that autonomous driving system, so the visual feedback is very important. Other than visual feedback, that other kind of audio visual feedback I should also tell, but visual feedback is more important. I mean, that is very fundamental. You have to identify objects, you have to identify roads, navigable roads, you have to identify the traffic signals. So, there are various tasks that a driver does if it is driven by a human being while driving the car. So, that needs to be resolved through machine intelligence. So, naturally, computer vision is a core subject domain or core subject area where all these theories are discussed and you have to apply those theories to develop this system. So, I hope this just emphasizes that the use of computer vision in autonomous driving system, which is an essential component. The fourth question is also a very general question, that is about suggesting that how a research candidate should approach in formulating research topic in computer vision. Now, in general, I should say that when you are going to formulate any research topic, you should understand the domain. First, you should understand the domain on which you are trying to do the research. So, you should have thorough understanding in that sense, what is there, what has been done already. And you have to also consider that what kind of problem you are trying to address. So, in a very abstract sense, there is a good intention of doing research, but finally, you have to read, I should say, a lot of research papers and subject matters in those areas and try to identify the gaps, what is there, how to improve different techniques, what are the challenges. So, you have to consider the problem which appeals you more. That is my suggestion. So, you should be passionate when you are choosing any problem. You have to be very passionate for solving it. If you don't have that passion, then you will not feel like exploring further. And then you read the background material, you prepare yourselves, find out what are the existing solutions and understand the gaps in those solutions, what is required and what could be achieved with the present state of the art techniques and algorithms. If you can understand that, then definitely you will be able to formulate a problem. So, research problem formulation is not a trivial task and it is not a job which you can do just for a few days work. You have to be continuously engaged in that domain, looking and understanding for the different challenges and problems associated with that domain. So, with this let me stop here for the questions which are already there, and if you have any other question, please you do ask me. The question is on computer vision. Can you elaborate more? Is it about the research? Can you elaborate your question also? I really did not get what you want. Your question is computer vision. Can you elaborate more? So exactly what you would like to know, please ask me that. Yeah, so I understand now the question what you are asking, that filtering, Fourier and wavelet transforms and image compression, color vision, feature extraction, pose estimation, visual recognition, something like that. You want to know about each and everyone's concept. Let me give a very brief overview of some of the things. I am not sure exactly what is your query, because it's very wide and it's very general. Like if you want to know the theory of filtering, you should learn about the linear system theory. That is the fundamentals, very basic, and where there are frequency domain or transform domain interpretations of filters. So, a filter, you can consider it's a system which processes input and which produces output, and this relationship between input and output, that can be determined by characterizing that system. So, mostly we handle with linear systems, where the impulse response of the system, if you know the impulse response, then you can compute to given an input signal what should be its output, and you know that operation is convolution operation. So, this is also a filter. Now, filter terms, it comes from the concept of frequency domain representation of a function or of a signal. You can represent a signal in terms of, say, linear combination of different sinusoidal signals or simple harmonic motions signals. So, in a linear system, when your input is a sinusoidal signal, your output will be also a sinusoidal signal. That is one of the property of a linear system, and whose frequency will remain same, but its phase and amplitude, that would vary. That in fact defines the characteristics of the system. So, that is what is frequency response. You should know for every frequency, signal of each frequency, how its output will get modified by, so how the amplitudes of that signal will be modified, that is a kind of gain or attenuation factor, and how the phase of the signal will be added to that part. So, that is the phase part, and that will give you a frequency response. So, filtering is that some of those frequency components of that signal will get attenuated, and some of them will be emphasized, will be enhanced. So, you are suppressing some of the components and you are passing some of the filters. So that is very essence, that is very basic for the concept of filters. Now, this can be understood very easily in one dimension. If you go through the books of linear system, as I mentioned, you can understand that. And for high dimensional signal like images, you have two dimensional distribution. So, there your filter responses also should be two dimensional. So, your impulse response would be two dimensional, your frequency response will consider. So, also the frequencies should be it should be also the basic components would be product of sinusoidal signals in every dimension, and depending upon the filter characteristics, those sinusoidal signals will be handled. The second concept, Fourier and wavelet transforms and image compression. So, in this case, these transforms are actually, you are representing the signal as a linear combination of some of the basis functions. We have discussed this thing in our introductory lectures on computer fundamentals to image processing, and then there is a part on image transforms. So, you know that for Fourier transforms, these basis functions are all sinusoidal signals, whereas for wavelet transforms, these basis functions are different. So, there are certain properties wavelets. So, properties of wavelets, particularly the basis functions, they are defined over a finite space, I should say a finite interval of the space on which they are defined. So, these are the wavelets, and if you express your signal as a linear combination of those wavelets, those coefficients will give you wavelet transforms. Now, the advantage of this representation is that you can establish certain kind of hierarchy of information representation. That means you can consider some of the components which are contributing most of the energies to the function or signal, and some of the components which are low contributing components. So, in image compression we try to exploit, or image or any signal compression, we try to exploit this fact that those components which are not contributing to the signal, we can ignore them, or we can also approximate them with much more with a higher quantization thresholds. Whereas the components which are responsible for reconstructing the signal, that all those things you can find out that which component is having more contributions by finding out the coefficients. If the magnitude of the coefficient is large, those components are contributing to the signal or images mode. So, you can have that kind of differential encoding of these components, and some of the components even you can truncate, and in that way you will achieve compression. That means you require less memory to represent the signal. So, instead of representing the signal directly in their particular domain, say either time domain or spatial domain, here we represent the signal in the transform domain. For example, discrete cosine transform is also one such transform where cosine basis functions are used, and those components are components of cosine basis functions. That means those coefficients of those linear combinations, those are encoded into the compressed stream. There are also other issues when you are compressing. It is the question of perceptual human perception, because many of the compressions are targeted for our perception. Say we want to compress image so that it requires less space, but when it is displayed, it should have the similar sensation, similar perception as it was in the original image. Though it loses information, that information loss will not greatly vary our perception of that image. So there are models by which you can define this kind of quantization masks so that differentially you can encode those coefficients. So that is also another fact which is used in image compression. And finally, the efficient encoding of any symbol using information theoretic concepts, like we call it entropy coding. Overall, that is a term. You should learn about entropy coding also. So that is used finally to efficiently code all those symbols which are used for representing a signal or image. So this is about the second one what you have asked. The third concept, color vision, there are two things. One thing is that how to acquire the the color information in the machine. The other thing is that how we perceive the color from our human perceptions, from the point of view of human visual system, how color is perceived in our perceptual systems in the brain using our optical pathway, optical nerves. So we discussed this part particularly, that there is a concept, there is a theory called trichromacy theory, where we can perceive color through the sensations of three different combined components of any optical signal. In our retina, there are three types of cone cells one is responsible for sensing the red zone of the spectrum, or we call it long wave zone of the spectrum. Another one is for sensing the green zone or middle wave zone and the blue zone. So, a combination of these three will produce the sensation. Now, if we can capture these combinations, if you can capture these combinations for a signal and those can produce equivalent sensation, so you will have the perception of the same color. So, following the trichromacy law, in fact, the technology has been developed for displaying of color and acquisition of color scene. So, as you know that for displaying of color, there are different display systems, and particularly in the color television, when there was earlier these cathode ray tubes are used. Even now those televisions are available where cathode ray tubes are used. So, there in the screen of the television there are three types of phosphorence materials are there, and the property is that if an electron beam hits that particular spot, it will illuminate with certain color. So, three colored phosphorence is there. So, for every point, every pixel, for example, information of every pixel where these three components are there, they are all co-located and they will be fired up. Conceptually, you can consider they are fired up almost at the same time. So, you get the sensation of that color. So, that is how the display is done. So, you divide it into three components. You represent color by three vectors, color primary colors, and then you produce the sensation as a combination of production of these three components. Whereas, while acquisition also you can use filters, optical filters, three wavelengths as I told, red zone, green and blue. These are the filters through which the same optical beam, through beam splitting you can do it, that can pass and captured independently by three different sensors. So, you can have three different components. Of course, I have also discussed another methodology for capturing color, color scene, color image, that is much more cheaper methodology in the technology wise because it is simpler. So, instead of sensing all the components at every pixel, here we place sensors for one of them only, but we do it in an interleaved fashion. That is called color mosaicing pattern. So, a color image is captured in this interleaving pattern, which is also predetermined, and later on using computations you can perform interpolations to get the full color image. We have discussed some of these methods. The other topic that you have mentioned, like feature extraction, you should go through the lecture on different techniques of feature extraction that we have discussed there. First was mostly what we need to understand, that which feature will be more robust to detect. Robust in the sense of it should be invariant to different kinds of transformation of the scene, and still that feature should be present and should be detected. So, that key point detection methods that we discussed, you please go through, and then how each key point should be described. There are different methods, so that description also should be unique. So, in another scene, if that particular point is that particular structure it exists, then the corresponding descriptors for the images of those structure, that should be also similar, so that you can establish correspondences. So, that is about feature extraction. I think I should stop here because other like pose estimation, visual recognition, those are some of the things which you will learn also through my lectures later on, when I will be, particularly when I am discussing this classification, clustering. Please go through those lectures, and later on there are deep neural architecture based methodologies. You may go through them. So, how cellular automata is used in image segmentation? I hope no, you have to read that part. It is not part of your course. So, please find out how cellular automata, what is cellular automata, and how there are some works on image segmentation. You need to read those papers. It is not a very common technique. It is not a very popular technique. That much I can tell you. There is a specific task related question, like in the image processing, suppose camera has 30 frames per second. So, in 1 minute 1800 frames. So, I want to decrease this size because of storage issues. So, what I do this for object detection on real time video. Yes, it is very challenging what you are saying. It is one of the I should say very essential task, or one of the challenges we need to solve, and it is not very trivial task. But no, there are various ways people do, and you have to consider the context of the problem. So, whenever you try to solve any problem using image processing, first look at the context. For example, you are saying that no, camera has 30 frames 1 minute in 1800 frames, but the question is that what is your scene? Is it a dynamic scene? Is it a static scene? And how first the objects are moving, and whether your camera speed is capable of capturing even that first movement of the object, whether this speed itself is sufficient. So, all these questions also you need to answer first, you need to find out. And naturally, the whole task of computer vision, one of the tasks, as you can see, that how to obtain the relevant information from the images, how to obtain key points which are relevant points which are distinguishing a structure, a scene from another scene, also which also tries to characterize that particular scene. So, all these methods, they are targeted at reducing the size of the data that you are handling and trying to make it more focused. You are trying to determine that set of data only which are required to solve your problem. So, you have to consider that also. So, when you are saying that no, you want to decrease this size, so I understand that you are considering the frame size, but the question is here, the question is that no, what kind of decrease, what is the decreasing policy? So, if you can identify the areas of interest, then without compromising on the resolution of the image, you can extract that particular region of interest and you can process it. That itself will decrease the size, and then you can apply those techniques of object recognition. So, here my suggestion would be always that look at the problem, look at the context, and accordingly you design a solution. The question is, can you explain Gabor transformation? Now, I do not know why this question has been asked, probably you require it. I would suggest please go through the textbooks. It is difficult often to explain Gabor transformation here. I can give you the conceptual part, then I hope that would help you to understand it. So, you see that Gabor transformation is nothing but you are using bandpass filters at different spatially located points. So, as if you are in your frequency spectrum, particularly if you are considering a two-dimensional frequency spectrum. So, you consider it is a series of set of bandpass filters, and they have a particular shape. Usually, they will have some kind of Gaussian shapes, or there are some functions for that. And you are trying to get the signal, get the component from them. So, and from there you are getting the coefficients. Once again, it's a you can consider it's an over complete set of basis functions, and the transform coefficients what you get, just the summation of the transform, all those summation of the superposition of those components will not give you the full, rather they will cover the whole signal, and no, it is not exactly giving you the full signal, right? It is giving more information. So, that much I can tell you. Now, to get the exact functional form and applying them, they are like filters. So, you have to just applying filters using those functional forms, and they are all set of filters, and you will get a series of signals which are the output of those filters, or the coefficients itself. That is what the transform coefficients. So, one first question is that in image processing, how can I find distance between any object and camera, and other question is that what is scale invariant and rotation invariant. So, for obtaining distance between any object and camera, as I mentioned that no, if you use stereo vision you can do it, we have already learned that part. For a single camera, there would be always a scale factor associated with that distance. So, you have to model, and no, there are some techniques by through calibrations you can compute this distance with certain restrictions. But usually in a stereo system you can compute this distance, but then also there also you need some calibrations to compute the exact distance. And what is scale invariant and rotation invariant? We have explained that part earlier also. Suppose you have an image and you have applied some processing and you are trying to detect some of the key points, say corner points of an object. Now, if I rotate the image, can I detect the same corner point by applying the same operations, whether the same corner points will be detected. So, if I can detect even after rotation the same corner points, then my operator becomes rotation invariant. Otherwise, it may be rotation sensitive, that means angular orientation sensitive. Similarly, scale denotes the resolution of an image. So, it depends that how close your object to the camera. If the distance is more, then the resolution is less for that image of that object. If the distance is smaller, is less, then the resolution gets larger. So, this is what is associated with scale. So, here also the same analogy can be drawn here, that you have a corner point in an object. Now, if I vary the resolution, that means while your imaging system, it can capture the image by when it is placed closely to that object or at a greater distance, at a larger distance, then the object's resolution, it will lose the resolution of representation, whether the same corner point can be detected there also by applying the same operations. If it is so, then you can say it is a scale invariant operation. I think I have discussed this question already, so I am not repeating it. It is kindly provide your suggestion on how a research candidate should approach in formulating a research topic in computer vision. As I mentioned that the steps are that you should know the subject matter, study it, and try to find out some problem on that which appeals to you more in that particular domain, and study it deeply, find out what are the state of the art techniques, understand what are the gaps in those techniques, what are the challenges, and accordingly you should formulate this problem. So, that was the summary of my discussion when I discussed this particular thing in the very beginning. So, we have few more minutes. So, if you want to ask some questions, please do it now. So, this question is for fast image processing, which algorithm is used, like YOLO or anything other. There is no particular solution to this. There is no such algorithm which you can definitely say it will handle all fast image processing cases. So, you need to understand, you need to find out that what is your task that you are going to solve, and look at the algorithms requirements and what kind of speed the algorithm could achieve. So, this question that it is not answerable in that way. You cannot say that any definite algorithm. YOLO is one algorithm which can perform object localization very fast, that we understand, but that is also not, that won't give, and that will not be sufficient for handling every kind of objects, every kind of speed of imaging. Okay, so you have to think about that. Now, this question comes repeatedly: which programming language is good for CV? Usually, as I mentioned, that C, C++, these are the languages which people used to do programming for computer vision problems. And then presently Python is also widely used. So, you can think of using those programs, those languages. Even Java is also used, but C, C++, Python are more commonly used. Can we get AlexNet another architecture in week 12? Yes, there are few architectures we have discussed. In briefly, we have discussed, of course. Yeah, I think AlexNet is also there. And how does satellite IP work? Satellite image processing. Right, it's it. I think once I have discussed this part particularly, you know that the satellite images, there are two types of images. One is called passive imaging, where you get the reflection of the objects from the ground, and those reflections are sensed through the sensors in the satellites, and you get the images. Now, there are different spectral bands over which these reflections are captured. So, for example, it could be optical bands like usual red, green, blue filters, or it could be infrareds, it could be shortwave, infrared. There are different kinds of spectral bands. So, this is how the satellite images, they have more number of bands. So, normally for a color image you have 3 channels, but in satellite image you have more number of channels, if I talk in the terms of channels. And then one of the key properties that is used to understand the scene, that property is the spectral property of the material. So, each material has certain characteristics that for some of the spectral zone its reflection is more, and for some of the spectral zone its reflection is less. So, from that characteristics now we can interpret about the material which is reflecting those energies in several bands. So, it is a combination of bands can identify what kind of material is there. But one of the problem of satellite image is that is the problem of resolution, because it is a very large distance from where you are imaging a particular scene. So, a resolution could be as low as, for example, a pixel could be of resolution say 30 meter by 30 meter area. So, a single pixel, it senses, it represents the reflection of an area of 30 meter by 30 meter, which is quite large. You understand that area of half a football ground area or quarter of a football ground area. So, from there, no, a single pixel is representing. So, there would be mixed materials. So, you are not going to get exactly which material is reflecting what amount. So, that is a problem. In fact, that is one kind of challenges, one kind of problem that needs to be resolved, and there are techniques to trying to solve that kind of problem. So, this is one kind of examples of satellite image processing using passive sensing. There are other kind of imaging systems, those are active sensing, where you shoot a microwave ray to the target, and then the reflection, whatever it is reflected, you sense that reflection, and by the amount of reflection, by the again that reflection depends upon the property of the material, property of the reflector, you try to analyze what kind of scene it is. So, these are called radar imaging, and in satellite you have various kinds of radar images, particularly synthetic aperture radar imaging is very popular nowadays, those are being used increasingly. So, their processing is quite different than what we process from this multispectral image or like optical images. So, with this let me stop here, because it is a topic which needs to be deeply discussed, which has various other facets. This question is once again on Gabor filter and Gabor wavelets for feature extraction. Can you provide some explanation? So, I just mentioned that Gabor filter is nothing but a filter, and there is certain properties of this filter that you need to understand, and that property is akin to an wavelet property, which means it has a localized spectral response. In the spectrum zone, it can localizes that spectral response, and also simultaneously it can localizes also the spatial zone. That is the wavelet property. It tries to localize both frequency and also spatial domain representation of a signal, characteristic of a signal. So, what you can do, you can apply this Gabor wavelets or Gabor filters. So, Gabor wavelets are like impulse responses, and Gabor filter is the filter which uses those impulse responses. It has its also corresponding property. So, you apply them with a certain it's up to you how do you define what kind of coverage you should have on the frequency spectrum zone, and accordingly you can represent them. As you know, output of the filter can give you in terms of the coefficients. So, what is the energy of the signal which has come out from the filter, which has been filtered. So, those coefficients can represent a signal. I think that should give you some idea. So, that is what will be represented as a feature. So, you can consider you can form a vector using those coefficients, and that can be itself represent a signal or represent a particular image. Then another question is that some insight on image quality and image reliability computations. I do not understand the question on image reliability. I do not understand that in what sense you are trying to say an image, the reliability of an image. Maybe you are considering that how it can handle the noise more. In that way, how robust is your technique? So, it is the noise handling properties of the images that you would like to know. So, definitely you have to perform this noise analysis and you have to see that your algorithm, how it performs with different contamination of different degree of contamination of noises. So, that is how one like to test and try to address this issue by incorporating different techniques to handle noise. So, maybe the image denoising, you can apply denoising before, that may again cause some other problems. And about image quality, there are different quality metrics that is used to judge the quality of your processed image, quality of your output, which is in the form of an image. So, one of the very popular quality metric is that when you have a reference image, then how close your processed image with respect to that reference image. For example, you are developing a denoising algorithms and you are handling images contaminated with noise, and you also know that what is a noise free image. So, if you process the noise contaminated image and try to get a denoised image, then you can compare denoised image with the noise free image, with the original image. This is just an example, and there is a metric called peak signal to noise ratio. I think I have discussed this metric in my lectures, so you can go through them. So, this is called the quality metric where you have a reference image, but there are other kind of quality metrics which does not require any reference image, which considers our visual perception of the image, how clear the image is. Now, for that of course, you have to read some of the papers which are dealing with image quality computations, and there are various models which have been suggested by which these quality metrics are computed. So, they are not as straightforward as computing PSNR, what we discussed in my lectures. I think this question is the last question because we have already crossed our time. And so, this question says that SARP uses box filters in the process of extracting feature vectors. So, can we consider that extracting feature vectors as an approximation to that of shifts? It is, you should not say it is an approximation, because finally you see that in the SARP, the descriptor, feature descriptor is used by different method. It uses Haar wavelets, and then it takes care of agglomerating the statistics of different orientations of the wavelets coefficient. So, descriptor is different. So, you go through the details, it is not exactly the shift descriptor. So, it is not approximation to shift. What you can say, box filter is an kind of approximation of computation of multi-scale, that difference of Gaussian computation. Yes, box filter is trying to approximate that part. Using box filters, we are trying to approximate that part. So, with this, let me stop here and let me thank all of you who have participated in this interactive session. I hope you are able to go through the lectures and you are getting some interest in this particular subject area. Thank you very much.